Good afternoon, ladies and gentlemen. My name is Stephanie Merry. I'm a member of the IMechE's board on the Power Industries division. The division represents engineers working in fields related to energy generation, power generation, which makes it very relevant to the topic of our webinar today. So may I welcome the audience to the webinar, which is entitled Tackling Net Zero in the Maritime Sector. It will cover electrification of ports and of vessel propulsion at sea. The webinar will consist of two presentations of about 20 minutes each, followed by a Q&A session. So please may I ask you to pose your questions throughout the presentation in the Ask a Question box on your computer. So to introduce the two speakers, firstly, James Hancock will open up, and he's the Innovation Manager at Swanbarton Limited. He's a data scientist focusing particularly on artificial intelligence with over 9 years experience in the energy sector. He will present his work on the PESO project. That's an acronym for Port Energy Systems Optimization, which was funded by Innovate UK. The project investigated how to use energy storage to enable ports to adapt to the current changing energy environment. Our second speaker is Brice Robinson, Manager of Naval Project Department at Brittany Ferries, where he's worked for the last 23 years. He's been closely involved with the design and construction of 5 new build ferries and also with maintenance and retrofit projects on the existing fleet. The subject of his presentation is shore power connection of vessels and hybrid propulsion for the reduction of emissions from vessels. So over to you, James, sorry. Can you start your presentation, please?
I can indeed. Thank you very much for that introduction, Steph. Right. There we are. So hopefully everyone can hear me and see this presentation. So yeah, today I'm going to be talking about energy storage and AI and how that's being used. Basically how we've used intelligent energy storage to help decarbonize the maritime sector. So why port electrification? We've got the pull factors, the incentives. So reducing cost, the cost of running fuel, of burning fuel, especially with the current economic climate, is very high. We then also have the net zero targets, trying to reduce greenhouse gas emissions. And then air quality is, increase the air quality. When you're in the center of cities, these ports often kick out large quantities of, pollutants that are bad for the local environment. But then also there's challenges that come alongside this. So what are the things that the ports have to face up to when they're trying to do this electrification? So limited grid access. These ports are often in places where they have limited connection to that grid. The second thing would be physical space. You can see from this photograph of Portsmouth International Port, where we did the PESO project, they don't have a lot of land. They're built right in the center of cities, or often built right in the center of cities, and they don't have the real estate to put in large amounts of stuff. And then finally, there's changing energy, changing patterns in energy consumption that are a big challenge for planners, trying to understand what's going to be required in the future, and not only that, but in what sort of form. So this slide here runs on from that. This is an increasing demand. You can see from 2019, we did some work modeling how the energy demands in Portsmouth International Port would change. And there's possibly up to a 30-fold increase in demand by 2040. But not only is there a massive increase in demand, but there's a massive change in the energy flows within the port. Currently, you've got single vector energy flows. You have grid just coming in as electricity and going to the loads within the port, so the lighting, the heating, all that sort of stuff. That's going to change. Not only are you going to have multiple incoming streams of energy, so you're going to have still your grid connection, but also renewable resources that you've got installed, so solar or wind or whatever it is. But you then also have a multitude of different uses of that electricity. So you might be not only using your hotel loads in your buildings, but also charging ferries, which Brice will be talking about, or charging EVs within the port, or customers who are waiting to get onto your ferry, or even running electrolysis to generate hydrogen to power other vessels. So let's look at another one of these challenges: grid constraints. You've got a massive increase in your energy that you know about, but your grid connection doesn't change size. Sometimes it can't change size. Sometimes it'll just be incredibly expensive to change that grid connection. So how do you do that without digging up the center of a city and spending all of your money? Now, energy storage is clearly going to be one of those one of the solutions to this, and it's the one that we support. Why energy storage? Well, first of all, it helps you use your renewable resources or your on-site generation resources more better. This diagram here shows that shows one of the problems with renewables. If you're generating more than you're consuming at that point in time, you either have to try and export it or you have to curtail it, which is waste. Energy storage lets you transfer that energy from a time when it would be wasted to a time when you need it, when there's a higher demand. Not only that, you can also reduce grid constraint by doing things like, for example, importing energy slowly over the course of the full day, so that you've got sufficient energy within the site to meet peak periods or high demand periods. Then there's also the financial question. Energy storage allows you to reduce your cost of energy within the port by using financial tools, for example, arbitrage. So you can buy low, sell high. That is, and when I say sell, you can either use it in the port at times when it would be expensive, or you can actually sell it back to the grid. For example, this graph on the right, it's the Octopus Agile tariff, outgoing tariff. So you can see that there's a period of time when the price of that electricity is incredibly high during the day. So if you have energy in your battery that you're not going to use, why not sell it then and generate extra revenue? You also will be able to reduce your network charges by, for example, either lowering your peak demand or avoiding things like triad periods. So and then finally, you can engage with balancing services. So these might be all the things that you're able to do in terms of balancing the grid. There's no reason why, as a port, you can't engage in those services as well. So managing energy, energy management challenge. What's that all about? Well, there's a lot going on here, as you could probably guess. There's different sources of generation. There's different loads at different times. You've got to forecast loads. You've got to forecast generation. There's a lot to do and a lot of non-linearity in this problem, and inherent errors that creep into things like predicting the future. And this all turns into a bit of a juggling act. And that is where artificial intelligence comes into play. So first of all, what is artificial intelligence? A lot of people talk about it, and I like a definition so that we're all agreeing on the same thing. This is a quote from the guy who basically wrote the book on artificial intelligence, Stuart Russell. And the two main things to pick up from this quote are, firstly, receives percepts from the environment. It basically receives information in from the environment around it, and then takes actions that affect the environment. So using the information that it's got from the environment, it does something to act upon that environment. So AI and energy systems. Energy systems are very complex. AI is very good at solving complex problems. Therefore, we like using AI to try and help solve these energy problems. And AI increases the resiliency within these systems by being flexible enough to be able to react to those stimuli that are coming in, to react to that information coming in, and then have a dynamic output on the far side. So what you've got is, in this picture, for example, we talked about the multitude of problems. What you have here is, say, for example, ferry schedules, you've got weather forecasts, you've got different financial signals coming in. What we're trying to do is crunch all of those features together and come up with the best way of effectively just charging and discharging a battery. And so this is the PEZO project. We've actually done this in the real world. We installed a 100 kilowatt battery into the Portsmouth International Port. It was a dual chemistry lithium-ion lead acid battery. And we built a system called EROS, which is what we refer to as our God in the sky. It's a cloud-based artificial intelligence that takes in all of the various different features about the site, crunches them up, comes up with this policy for how to charge and discharge the battery, supplies that to the port, and then the port can use that energy resource to maximum efficiency. And this is the results. Now, admittedly, this doesn't look like much because the battery was quite small in comparison to the size of the total load of the site. But what's really interesting about this is where the green line is in the middle. So I'm just going to put my laser pointer on. This sort of green line here, that's the zero line. So that's no energy going through the site meter. Now, positive is export, and negative is export, positive is import. So what you've got here is you've got energy being imported, and then you can see that at this point the solar arrays start to jump up for the day, and then you've got export out of the site and then import again. But this point here, if it was a dumb system, it would try and start exporting the moment that it had solar available. Basically, it would just try and instantly push that solar energy out. What it in fact does is it waits until later in the day when there's different price signals available, and it views this as the optimal time to do that charging regime on the battery. And then in the afternoon, again, it doesn't instantly start discharging the battery the moment the site has to start importing. It waits until peak tariff periods. And you can see here, it's just chopped off a big chunk of that energy that would have had to be imported at the peak prices. So out the back of this, we also developed a tool called ASCOT, which is our digital twin of the site. ASCOT it's not just a digital twin of Portsmouth, it's a digital twin of any energy system that you want to model. And the idea is that it can model complex situations using our algorithms, using that EROS tool that we built for Portsmouth to optimize your system, recommend or size a battery correctly for that site. And then when you're actually in operation, enables you to have an early warning system when you can predict what sort of things might push your site towards site boundaries or breach other constraints that you've got. And so finally, what is next? Well, this system is not just applicable to the maritime sector. It can be deployed in any sort of environment where you have a need for storage and you want to optimize and increase the efficiency of that storage. So for example, we're currently now working on a project called GRIPS, where we're installing a solar storage system in Kathmandu to try and displace diesel backup generation in regions with low grid reliability. And you can imagine that that's a system that is deployable across the entire developing world, or anywhere, in fact, with weak grid connections. But this is also equally applicable in industrial settings and in agricultural settings. And it's applicable, as I said, both in the UK and abroad. And that's everything from me. Thank you very much for listening. My name's James Hancock. If you've got any more questions, be very happy to answer them in a bit. That's everything from me. Brice, I will stop my presentation now and hand over to you. Thank you.
All right, thank you, James. I don't know if you can hear me. Okay. So I will start my presentation. So first of all, I'm a naval architect and project manager at Brittany Ferries, and so I'm in charge of let's say thinking about the future of the ferry designs and as well of how to adapt the current fleet to let's say the necessity of using shore connection power. So I will share my screen now. So here we are. So first of all is why. Sorry, I have. So my slide is not shifting from one page to another. Sorry for that. I will try again. Yes. Okay. Let's try again. Yes, sorry. Here we are. So why are we trying to connect ships alongside when they are berthing? It's for several reasons. So it's to limit the pollution because, as you know, the conventional fuels are let's say, emitting some pollutants such as NOx and SOx and particulate matters, which are not very good for the neighborhood of the harbor. And also the engines producing electricity while the ship is at quay are also generating noise. Furthermore, the rules evolution, such as FuelEU, will soon impose ships calling more than 2 hours to connect to the shore grid and stop their engines, or they will have to use decarbonized energy such as fuel cells, batteries, or any renewable source of energy. So ports are starting to investigate these subjects, such as Portsmouth and Brittany Ferries, since we are one of the main ferry operators using Portsmouth Harbour. I've started to, let's say, look into those retrofit studies on 7 of our existing vessels, following the norms which has been developed for that, which is IEC 80005 norms, which is defining, let's say, 3 different segments of ships that will have to connect to shore from 2030. And one of the segments is ours, is let's say what we call RoPax or RoRo. The 2 other segments are containers vessels or cruise vessels. And for the ferries, the requirements is to supply current in 11,000 volts or 6.6. With a power requirement of up to 6.5 MVA, which is quite a lot, and also have this current available in the 2 frequency which are commonly applied on board ships, which is 50 or 60 hertz. And for the, let's say, ferries, let's say the amount of power which could reach 6.5 MVA could be, let's say, taken onto 1 cable only. Here is the list of ships that we are thinking to connect at quay. So this is basically most of the Brittany ferry fleets, which is up to 9 vessels. And some of them are already, let's say, sailing and are not at the moment ready for, let's say, for shore connection. But let's say it's something that we are planning to activate very soon by means of retrofit. We will see that later in the slides. And you can see also we have two ships in the middle of the list, which are the Saint-Malo and the Normandy 2. Which have quite a high demand in terms of power. And the reason for that is that those vessels are meant to be fitted with batteries and so that we could, let's say, use hybrid propulsion. What is the hybrid propulsion? So it's a ship which is equipped with batteries, is in fact able to store quantity of energy, electrical energy. And on those two ships, each of them will have a capacity of 11 megawatt hour, which would allow them to use their propulsion on electric mode during harbor maneuvers. So on top of, let's say, the call, where the ship will be connected, the maneuvering will be done also in electrical mode, preventing, let's say, reducing the amount of pollution in the neighborhood of the harbor, which is, of course, let's say, a benefit for the population nearby. So the other ships, which are, let's say, conventional, will, let's say, connect during the call. And you can see that there is a variety of power demand. We have indicated for each of them the average power and the maximum, and the estimated call duration per year. So that shows, and it's a link with James' presentation, which also, let's say, highlight the difficulties of, let's say, providing the systems that can cope with the peaks, because in Portsmouth, we can berth up to 3 vessels at the same time, and which means that potentially we could have 2 hybrid vessels taking up to 6.5 MVA each, plus a conventional one up to 3 MVA, which in total makes quite a lot of power. So now we're going to look how concretely we are bringing the electricity to the ship, because that's once, let's say, you have bring the necessary power, like James has explained in his slide, or show some example. We need also a system that brings the shore power cable to the ship. And that's at first could be seen as being quite a simple thing to do, but it's in reality not that simple, due to the fact that each ship is a bit different. The shore connection door is not located at the same place. And we have a particularity on ferries, since we are berthing using ramps for vehicles. Longitudinally, we have to maintain the ship in a fixed position, which means that the system bringing the power to the vessel will have to be able to, let's say, bring the plug at the correct location. And we need to cope with, let's say, longitudinal translation, so that the cable can bring, and the plug can be bring just above the shore connection door. And also we need to cope with other details, such as tides in some harbor, which can be quite high, and as well as other obstacles and other things and features which are on the quay, which are not sometimes big enough to, let's say, welcome such a big installation like you have on the image at the bottom of the page, It's an example of a shore connection facility in the port of Southampton. The next slide is it shows how a shore connection can be made on an existing vessel. The blue parts are representing the different rooms in order to, let's say, be able to connect the ship. So the first main items are the shore connection rooms or the plug rooms, and they are positioned on both sides of the vessel, aft and forward. Why do we have 4 rooms? It's because simply the ship can berth on starboard or port side, and also can be stern first or bow first to the ramp, and that's why we need those 4 plug rooms. Then we have an additional room, which is which we call the transformer room, that you can see in the garage of the vessel here, and this contains the transformer that will let's say transform the current from 11,000 volts to approximately 400 volts, depending on the voltage used on board. And in front of it, we have high voltage protection cells before let's say we connect the current, the cables to the main switchboard of the ship. And the main switchboard of the ship needs, of course, to be extended in order to, let's say, so that we can insert the necessary breaker to the rest of the ship net. So here is a calendar of, let's say, our retrofit vessels. So we are planning to, let's say, carry out those retrofits from between 24 and 27. And now we can play a video showing you how we can connect the ship. And Fiona, if you may play the video, please.
Coming into port.
Hi Brice, this is Fiona. The video is now playing.
Yes, thank you, Fiona. So here we are in the port of Marseille, and we have a ferry from Corsica Linea, which is a ferry company operating between France and Corsica. And you can see the size of the IEC plug, which is a standard that has been developed. So the plug is being connected, and then after we have an automatic synchronization with the auxiliary gensets of the vessel in order that the connection is made. So thanks for the video, and that's all for my presentation.
Many thanks, James and Brice, for quite fascinating presentations. I'm particularly interested in the stuff that Brice was saying about how you actually managed to get an electrical cable to connect to your ship. It's not quite the same as my little motorboat where I just get an ordinary 3-pin plug and plug it in. And equally interested in what Jamie was saying about all the different aspects that you have to take into consideration when you have a shore power with batteries and so on. So we've got one quite long and complex question so far. If I can try to summarize it, I think the issue that Alan Dixon of Calmac Ferries is asking is, how do you manage the transfer seamlessly when the ship's loaded on shore power to its load on its own generation system, without having a blackout, which is going to make sort of getting running again rather difficult? I think probably Brice, you're the best person to ask that one at the moment.
Yes, Thanks for the question. Yes, it's an important point because you may lose quite a lot of time and create some troubles if you are missing that phase. And in fact, you will need to revise your power management system on board to allow, in fact, an automatic synchronization between the shore power and the ship's power before you could actually disconnect the auxiliary genset. So if you have one auxiliary genset, it's quite simple. When you have two, it's a bit more complex. And there are, let's say, the automation specialists such as ABB or Partila or offering system for that. And it allows a smooth transition between the shore power and the ship power. And it can be made within approximately 20 seconds, the synchronization.
Oh, that's very fast, isn't it? Wow.
Yeah, it's quite fast, yes.
Yeah. James, have you got anything you can add to that? Does it really relate to your work?
Not massively, no. It's I mean, the only thing to consider is that when that ship takes up that power, there's got to be that power available within the port, and so not only blackouts on the vessel are things you've got to worry about, but also if you get massive spikes in demand and your grid connections can't cope with it, you might end up blowing up transformers, and clearly that's not something that anyone wants to happen.
No. Okay, so yes, that is very difficult, isn't it? Does your AI system cope with that?
Yes, I mean, the entire point of the system is you've got to be able to predict when these things are going to happen, and so yes, there's our AI system predicts when those loads are going to be coming in, so that there's going to be sufficient energy, for example, in the storage to be able to cope with that additional load. But then you've got the actual battery management systems that will be able to provide that power as quickly as it's needed. So yeah, so that would be supplied by the manufacturer of the actual hardware itself.
Right. So Brice, Brittany Ferries goes, I know, St Malo and Caen as well, does it? Is it Caen?
Yeah. Yes, that's right.
And Portsmouth.
Many other destinations. Yes, we are also going to Plymouth, to Poole in UK, and Roscoff, Cherbourg, Saint-Malo, Le Havre, so Ouistreham, like you said, and we are going as well to Spain.
And
so
do all these ports have the facilities for you to connect to shore power? Is it only Portsmouth, and you said St Malo is doing it?
Not yet. They are working on it. Like Portsmouth is starting to do also his own investigations about that. But things are moving ahead, and let's say we are expecting by 2025 having the first ports being ready for shore connection. We will have Bilbao in Spain. Probably Ouistreham in France, and we are hoping Portsmouth and St Malo as well, because this is, let's say, where our first hybrid vessel will sail. And if we have, let's say, the proper power for those ships, we can save up to 12 to 14% of conventional fuel, thanks to the shore connection.
Okay. And the work that you're doing, I mean, you mentioned, I think it was 2030 Fuel EU. Is that an EU directive?
Yes.
Would you have done this without the directive?
Sorry, Steph.
Would you have done this work without the directive?
Let's say probably not as in such an extensive manner. But for sure, we will have to consider it for a new build vessel, because let's say you have Fuel EU, of course, which is one thing for the shore connection, but you have also something which is called the CRI, the Carbon Intensity Index, which is a new rule which is starting to come into force this year, which will force ship owners to reduce emission of their vessels and it's rules which, let's say, which has been, let's say, put in place by IMO. And the aim of that rule is to reduce by 70% the level of greenhouse gas emission by 2050. So it's quite a huge effort that we have to make. And using electricity as an alternative fuel is one of the solutions to reduce CO2 emissions. So for new ships, definitely shore connection is a way to the future.
Okay. Well, yeah, that's interesting. Of course, UK is no longer part of the EU. So, Jamie, do you know, is there anything similar in Britain? Can you unmute?
So yeah, no, absolutely. In terms of directives, there are various. So in Portsmouth specifically, there's a directive by the city council that's trying to increase the air quality in the city, and so the ports have to comply with that. So there's local policy, and also there's the 2035, just cutting emissions that everyone's trying to comply to.
Yeah.
Yes, the cutting of emission is worldwide.
Yeah.
Brexit or no Brexit.
Brexit or not, indeed.
Yeah, so it's interesting. So I'll ask you separately on these questions. Brice, do you think that the EU is doing enough to support this directive? Can you get finance or resource support to do the work, or do you just have to bite the bullet and the company has to pay?
It's not very easy. Yes, let's say it's a huge effort that each ship owner have to do, and finding co-financing and grants for making all this is I would lie if I would say it's easy. Some ports have managed to co-finance their future realization for shore connection, such as Bilbao, which include not only the development of shore connection, but also a source of renewable means of electrical production. And if you go for this on green electricity, yes, it's easier to get some heads, financial helps, but it's not an easy job. And the demand is high, and it's not something which is so easy to realize.
No, it's not.
I can give you some figures if you like, just to continue on that subject. Let's say retrofitting of an existing ships, like I've just shown, is approximately a cost of 2 million euros per vessel. And the cost of shore connection power, figures that we are, let's say, sharing with various ports, is in the range of 1 million euros per megawatt of power. So that's a very rough idea. So we are speaking about 6.5 MVA, which is equivalent to 5.2, 5.3 megawatts. So each connection is approximately a cost of 5 to 6 million euros.
Wow. Yeah.
So it's a lot of money.
So Jamie, if I asked you the same question, I do know that your PISO project was funded by Innovate UK. Is there much more going on to help?
Well, there is obviously continuous funding in this sector, and the British government have got several bids open at the moment for doing further work like this, particularly scaling up the PESO project. And we very much hope that we will be able to demonstrate the work that we did at PESO on a larger scale. But as you say, we are reliant on government funding because at the moment this is incredibly expensive work and it's still not proven at scale. So the next steps on this are absolutely critical for the persistent ability to provide shore power in the UK. We really need to prove this, and we need to prove that we can do it economically as well, because there's, as Brice said, it's the ships are expensive to upgrade, but if you need to upgrade your grid connection by the numbers that Brice said, and Portsmouth have estimated many megawatt increases that might cost, well, a lot of money, millions of pounds. And so you have to be able to justify the work that you're doing on a commercial basis.
Okay. Right, we've got some more questions here. First one's from Rebecca Taylor, who's the Environmental Policy Advisor to the Scottish Government. And that's a question for you, Brice. Will the ferries eventually become zero carbon propulsion for all sailings, not just manoeuvres?
But that's the aim, step by step. It's not easy. I would lie if I would say so. Getting rid of conventional fuel is very expensive because zero emission vessels are extremely costly in terms of first new machinery type, which are not very well, let's say, distributed yet. If you like to use zero emission engines, for instance, you don't have such a big range of power available. Let's say, if we speak about fuel cells, if we are speaking about methanol engines, which are capable to use that type of new fuel, so the demand for let's say reduction of greenhouse gas is high, but the mean to reach it is are not very let's say accessible yet. In terms of like I said, in terms of machinery, and secondly in terms of availability of new fuels such as methanol, ammonia, or bio LNG, which are carbon-free fuels. And that's why also we think that the economy we need to adapt to that situation. And the first level on which let's say the ship operators can play on, it's the easiest one is the speed of the ships. So the ships will have to reduce their speed. We trust that we will see that in the coming years. And secondly, yes, we will have to find alternative ways of producing energy. And it's a high mountain we have to climb, very high.
I think that's something the population has to accept, doesn't it? As you say, going slower or whatever.
Yeah. Yes, yeah. And still pay more for it. That's also the problem, because let's say we've been used to fast connection and cheap energy. We never find something as easy to use as a conventional fuel. That's very clear. Yeah. In terms of let's say practicality, in terms of cost, it's unbeatable. But to remove the pollution it's a huge challenge, and we need to adapt to that.
Right, it's quite a lot of questions now.
Just to jump in on something, sorry, Steph, just to jump in on something Brice said there. In terms of bringing the cost down, I mean, that's one of the things that our system is specifically trying to do, is lower those costs of energy. We work in the developing world as well as in the maritime sector, and we're very aware of the fact that people who don't have very much money aren't going to be spending more just because it's green. That simply doesn't, if you're struggling to feed your family, you're not going to be worrying too much about the long-term climate implications. And so we do view it as absolutely critical to the work that we do to try and tackle the environmental challenges that the world faces at the moment, but doing it in such a way that it brings that levelized cost of energy, that the actual price of you pay for a kilowatt down to a level that is competitive with current energy prices.
Right. Okay, let's move on. Nicholas Boyd has asked, navies have been using shore power for over 100 years, including synchronization with the grid. Did you learn anything from what they've been doing? And I know you've got the Portsmouth Navy involved a bit with your project, haven't you, Jamie?
Yes. Yeah, no, they were advisory, and they were very interested in what we're doing, because they're keen to learn from us. Whilst the Navy have been doing this for a long time, we're doing stuff that no one's done before. So I think there's strong mutual learning going on between the Navy and us.
Oh, okay, good. Yeah, don't want to reinvent the wheel. All right, Ian Borthwick has asked, can you, Jamie, enlarge a little concerning the external boundaries on your modelling? Can you see the whole question? It's a bit long.
It is. So, for example, the overall demand at the dockside from both shore and ship. So, I'm not entirely sure what this question means, but I believe that it's relating to what is it that we monitor specifically within the port, and the answer is, so we monitor quite extensively across the port. The port's invested quite a lot of money in monitoring equipment to be able to see what's going on at all of the points, and we actually spent quite a lot of time doing that as well. So we will be we monitor each of the individual. So there's a distribution of substations. We monitor within the port how the energy flows throughout that, and then we've got local weather stations on the port that see the local, to get the local meteo data as well as forecasting that you would expect, and yeah, anything that we can get hold of basically that is relevant. So as you said, the shore powering, well, when vessels come on, we will be monitoring those. There aren't currently shore powering vessels at PIP. Well, there is, but it's running, well, it's not really relevant. Yeah, so I think that answers your question, but probably not very well. Well, there's the time of year. Of course, there is time of year variation. We do seasonal modelling because that would be a standard part. So we've got quite a large amount of temporal data. There is actually a really interesting problem with the temporal data from the port, which is something that machine learning is, as a sector, is having to tackle at the moment, which is we've got 2 years worth of data, but half of that data came from during the COVID period. And so actually trying to model port activity with data that was collected during when COVID was happening means that all of our models are skewed, and it's quite an interesting technical challenge to undo that. Yeah, I hope that answered your question.
Okay, well done, Jamie. Right.
Sorry, I think so. Ian just expanded that question slightly, asking about the implications of refueling with hydrogen from a tank. We're actually also involved in a slightly separate project called the SPINE project that is looking at these multi-vector fuel situations. So the modelling actually takes into account not just the electricity flows throughout the port, but the multi-vector. So how do you get the ammonia through the port? How do you get the hydrogen through the port? And how do you model that flow of energy into hydrogen and then onto a vessel? So those are additional parameters that we're trying to tackle at the moment as well.
Oh, okay. Well, thank you for pulling that one out. There's a question about certification from Tom Matthews. I think this might be something you would be able to answer, Brice. Sorry. Do you have to get the system certified by IMO?
Through the classification society of the ship, yes, it could be Lloyd's Register, Bureau Veritas, or DNV. Yes, of course, it has to be checked by.
And how easy has it been? Is the question.
How easy it is? In fact, the technology of shore connection is not that complicated. It's let's say when I show you the layout of the ship, so you have plug rooms, you have a transformer, you have HV cells. You are basically using the HV facility in order to have only one cable and a small cable to connect to the vessel, because if it would be medium voltage, will be let's say it won't be a cable, it will be pipe. So it's so in fact, once you have, it's not a very new technology, the shore connection. It's something which has been used already. No, the difficulty is to bring the current at the berth, at the correct location, to have a mobile system that allow, let's say, to bring the cable at the correct location, because it's stupid, but if the cable is not at the correct location, you have no electrical power. It's like an electrical car. If you don't have power station, you have no fuel. So it's all this that we need to develop, and it's not really a real technical challenge on that aspect. There are things which are more complex than that, I would say.
Yeah. So I think that answers Ian Reynolds' question. Are shore management systems readily available? Okay. Alan's back on again. I'm getting feedback. Please could somebody mute themselves? Alan says, Brice, I saw that each of your ships accepts 11 kilovolts. Do you think the port should be required to provide a voltage vessels turn on rather than vessels having to fit additional transformers on board?
I didn't get the question, sorry, Steph.
He says that each of your ships accepts 11 kilovolts input.
Yes.
Do
they
you
are all, yes.
Port should be required to provide a voltage that vessels turn on? I think that's where it says, rather than vessels having to fit additional transformers. Have you got additional transformers?
But we have one additional transformer indeed, because let's say we are not using 11,000 kilovolts, 11,000 volts, sorry, on board. We are using, generally the nominal power on board is 380, 440. We have also 700 volts sometimes. So of course we have a transformer, and it's one of the feature we need to integrate for retrofit for shore connection. Yes, we have a step-down transformer.
Okay, what's two questions? What is the energy to weight space ratio advantage and commercial advantage compared to conventional energy? So I guess we're talking about the
batteries.
High-speed ferry. Do you have any high-speed ferries?
No, we don't. Well, let's say we don't have any more high-speed ferries. We used to have one which was called the Normandy Express. It's IMechE catamaran, but we don't have it anymore. So the problem of, let's say, I'm not too sure about the question. So would we be able to use batteries on a fast ferry? Is that the meaning of the question, you think? Or?
I'm thinking that the way I interpret that is they're saying the batteries have to take up a lot of space, which could be used for cargo.
So, of course, the batteries are taking some space, but they are, in fact, limited in size and power. Let's say 11 megawatts of battery capacity basically gives you approximately 2 hours of propulsion. So it's not enough to cross the channel. And the batteries are located in the double hull. Let's say we have let's say some side compartments let's say which are necessary for the stability of the ship, which are voids. So basically we are not reducing the commercial capacity of the vessel. In terms of weight, so 11 megawatt of battery represents approximately 200 tons of weight, which is let's say a reduction of dead weight of the ship, that's for sure. But a dead weight of a vessel like a medium-sized ferry, like operating on the central channel, is in the range of 5,000 tons. So you remove 200 tons out of 5,000 tons. So it's still, let's say, it doesn't harm so much.
Okay.
And it and you should see that like the Toyota hybrid type. I don't know if you are familiar with Toyota cars. They don't have a big battery capacity. They are here to, let's say, remove the peaks of consumption and let's say smooth the slow driving. So it's a bit the same on our ship. If I may take that comparison, which is of course a bit simplified, but just to give you an idea of it.
Yeah, okay, that's helpful. It's an interesting point. I think there's Anthony Florida James, but unfortunately he's gone now. And I think, Jamie, you answered that question really, didn't you? Any of the ports actively planning for ammonia, for example? So looking at
Yes.
low carbon fuel.
Yes. Yes, we are, as I said, we're involved in that Spine project called Spine, which is actively looking at alternative fuels that ports will use. Because obviously, you know, we've talked today about the electrification of vessels and how to do shore powering, but in a potential multi-vector fuel environment where some boats might be on methane, some boats might be on ammonia, some on electrical shore power, how do ports prioritize the investment in the infrastructure that they're going to be putting in? Obviously, you don't want to have stranded assets where you bet the farm on hydrogen, for example, and people only want ammonia, or they're not interested in those sort of fuels at all, and they just want electric. So this sort of modelling work is actually critical to what we're doing at the moment to try and help ports understand that environment, to understand what the cost of certain decisions that they will make will be. So yeah.
Okay, I don't think there are any more questions, which is just perfect because we've got 3 minutes left. So can I thank Brice and Jamie for their really interesting presentations. I was fascinated by some of the problems that you brought up, and wish you both all well in your work. And thank you to all our attendees for listening to us today. And I hope you have enjoyed the seminar as much as I have.
Okay, thank you, Stephanie. Thank you, James.
Thank you, Steph.
Thank you, everyone. Thank you, Fiona, for helping us. Bye.
Bye.